Welcome to the 10th episode of our series, The Mother Earth. We have learnt in episode 9 that the Earth acquired its strong and stable magnetic field soon after it underwent the process of core formation. The magnetic field, also referred to as the geomagnetic field, originates in the outer core, which is constituted of electrically conductive Fe-Ni-rich fluid matter. The elements Fe-Ni and other elements that accompanied them segregated in the core of the protoplanet Earth are primordial assets acquired during the accretion process. The amounts of these accompanying elements, like the radioactive elements, sulfur, and some of the transition elements, varied amongst the terrestrial planets and the V-type asteroids that accreted directly from the solar nebula. That is revealed by the difference in their densities and the core sizes. The size of their fluid outer core decided the strength and expanse of their respective magnetic fields. You know that Mercury has a large core, but because of its small fluid outer core, it has a much weaker magnetic field than that of the Earth. The strong magnetic field of the Earth originates from about 2,900 kilometers depth below the Earth's surface, that is beneath the Gutenberg discontinuity. The seismic boundary extends for less than 10 kilometers, but distinguishes the solid mantle from the underlying fluid outer core. The magnetic field is self-generated and self-maintained, caused and supported by the complex convection currents in the outer core, and most importantly, by the continuous supply of radiogenic heat from the inner core. The continuous dissipation of heat, as we learnt in episode 9, is owing to the radiogenic decay of isotopes like uranium-238, thorium-232, and potassium-40. Their half-lives are much longer than the Earth's age so far. Therefore, the heat dissipation from the inner core should remain effective for billions of years ahead. Imagine what would have happened if it weren't so. The continuous swirling movement and the complex spiral paths of the convection currents within this ferromagnetic fluid system is due to the turbulence caused by the Coriolis force exerted by the Earth's unique spin rate and by its axial inclination. In episode 1, we learnt how the physical parameters of terrestrial planets differ, didn't we? These differences too have a different direct effect on the strengths of their magnetic fields. The spiral convection induced by the Coriolis force generates electric current. Since iron-rich melts happen to be excellent conductors of electricity, the kinetic energy secured by the outer core fluid system gets converted to electrical and subsequently to magnetic energy, since the convecting matter is ferromagnetic. This process of energy conversion from kinetic to electrical and to magnetic energy is in a way similar to electricity generated by a dynamo, which converts mechanical energy to electrical energy. The kinetic energy drives the convection currents efficiently to a height of about 1,700 kilometers, well up to the mantle core boundary. Approaching it, the uprising fluid cools, dips, and travels downward, partly solidifying and also chemically differentiating. Sinking under gravity, the potential energy gets converted into kinetic energy again. The partly solidified ferromagnetic matter melts and absorbing also the heat from the inner core, it travels upwards again. Thus the convection continues uninterruptedly in the outer core. So is maintained the magnetic field of the earth. The convecting fluid loses heat partly also to the rocky lower mantle. Since the rocky mantle formed a poor heat conducting medium, the transmission and speedy loss of heat was prevented. The heat conserves the fluid state of the outer core and thus indirectly protects the generated magnetic field. The Earth would have become another frozen planet like Mars had it not been so, and of course would have lost its magnetic field. In episode 8 and 9, we learned that the inner and the outer core matter segregated under very high pressure and temperature conditions. In such conditions, many elements like cobalt, copper, antimony, as also the radioactive elements uranium, thorium, potassium, got incorporated in the compositions of FeNi metallic alloys in the inner core and as sulfides in the outer core. These metallic and sulfide dissolved compositions indicate that their separation in the Earth's nebula was accomplished in oxygen-poor environment or in reducing environment. In iron meteoroids also, if you recall, the mineral and chemical compositions point to their melting and crystallization in similar oxygen-poor environment from chondrites in the asteroid zone. Comparable conditions should have prevailed in the nebular mass of each terrestrial planet and in the V-type asteroids while their cores were formed. Simultaneous with the separation of the core, the elements like silicon, oxygen, and other lighter elements in the nebular mass were expelled and displaced outwards. They readily formed the silicate minerals like olivine, pyroxene, and feldspars, accommodating elements like magnesium, iron, calcium, and aluminum. Oxide minerals like magnetite, chromite, and ilmenite, comprising of the elements like iron, nickel, cobalt, chromium, titanium, were also formed. The crystallization of mantle minerals was accomplished in oxygen-rich environment. This shift in the redox conditions, along with the density separation, compelled all such elements which have more than one valency, especially the transition elements, to reposition themselves rapidly in the solid and fluid core and in the minerals of the solid mantle. Way back in 1923, the two geochemists, the Norwegian V.M. Goldsmith and the Ukrainian Vladimir Vernadsky, took cognition of such process of core mantle fractionation, drawing analogy with the findings on meteorites. Marking the distinct difference in association of certain elements in iron meteorites and achondrites, Goldschmidt put forth the geochemical classification of elements into the siderophile, that is iron loving, the chalcophile, that is sulfur loving, the lithophile, that is oxygen and silica loving, and the atmophile, atmosphere loving groups. This fractionation, chiefly guided by the elements iron, sulfur, silicon, and oxygen, was referred to by him as the earliest natural experiment in space. This geochemical fractionation and gravity separation was rapidly accomplished within only a few million years of the existence of the proto-Earth. The magnetic field of the Earth became active ever since the thermal gradient in the core stabilized and the separation of the metal-rich core from the silicate and oxide-rich mantle was accomplished. Life evolved a billion years later, but that it could step in was primarily consequent to this exceptionally different pre-planetary history of the Earth. The spatial spread of the Earth's magnetic lines or curves resembles the pattern of magnetic lines of a dipole bar magnet. Therefore, an imaginary dipole bar magnet is assumed to have existed inside the Earth, its poles aligned approximately with the geographical north-south poles of the Earth. Centuries ago, about 600 BC, the navigators detected that the magnetic north pole indicated then by the lodestones did not exactly coincide with the geographical north pole. At present also, the directions indicated by the modern compass require the declination correction to locate the two geographical poles. At present, the Earth's magnetic axis makes an average angle of 11 degrees with its spin axis. It keeps changing and it flips also. That is, the magnetic north becomes the magnetic south. But the property that magnetic or ferromagnetic minerals orient themselves according to the magnetic poles gain extraordinary importance in the last 6 decades. This influence of the magnetic field on minerals was marked in crystallized lavas, in minerals crystallized out of hydrothermal fluids, or during their transport as sediments, or when hung in air like a navigator's lodestone. Frozen in the rocks, it was referred to as the paleomagnetic record. Marked in the successively formed Hawaiian lava flows, it provided additional data revealing the history of seafloor spreading. even in space exploration. The paleomagnetic data on Martian basalts, 3.7 billion years old, provided proof that the planet had a strong magnetic field about 4.2 to 4.3 billion years ago. The magnetosphere around the Earth extends for about 10 lengths of the Earth's radius towards the Sun and about 100 times the radius away from the Sun. You are familiar with this scale of measurement, isn't it? The Earth has about 6,371 kilometers long radius. This distorted and asymmetrical shape of the magnetosphere is caused by the flow pressure of the incessantly bombarding electrically charged particles of the solar winds. Extending beyond 400 kilometers above the Earth's surface, the magnetosphere deflects these solar winds, harmful to life. Besides, it saves the Earth's atmosphere from getting eroded away by these solar winds. Imagine what would have happened if this safety cover wasn't there. The Earth would have looked barren as Mercury or as the Moon. Life wouldn't have had a chance to get roots on its surface. Leave aside its survival on Mother Earth. What have we learned in this episode? We have learned that the magnetosphere 400 kilometers above the Earth's surface owes its continued existence to the uninterrupted convection currents in the fluid outer core. The Earth's core formed in oxygen-poor or reducing environment, while the mantle formed in fairly oxidizing environment. This shift in environment compares well with the changing environment in which the iron meteorites, stony meteorites, and achondrites were formed in the asteroid zone. The separation of core from the mantle compelled many elements to reposition themselves in metals, in the sulfide-abundant fluid core, and in the silicate minerals of the mantle. The magnetosphere deflects the charged particles of the solar winds, which could have eroded away the Earth's atmosphere, invaluable for life. The magnetic or paleomagnetic record of the magnetic field reversals preserved in minerals of the seafloor has provided proof for the phenomenon of seafloor spreading unique to the Earth. We will look at the Earth's atmosphere in the next episode. Thank you.